Okay, let's go through the process of solving a linear system again. What I'm going to do is I'm going to demonstrate it. Then I'm going to ask you to go through and solve a couple of problems too. So here, let's write down a linear system. Let's say we have x plus y plus z equals 6, and say x minus y plus 2z equals 4, and say minus x plus y plus 4z equals 8. I have no idea what the solution is. So here's our linear system, and what we want to do is we want to, and this is how we always put it in the standard form. We have a linear combination. You see, it's a sum of terms. There's an implicit numerical value, 1 in front of each of the variables. We have a single variable, not to the power 2 or minus 1. And the x's are lined up, the y's are lined up, and the z's are lined up, and this column is lined up. And we never change that. We're doing Gauss's method. So Gauss's method involves making one of 3 row operations, in which the strategy is you want to get to echelon form, which means you first want to usually clear this first column. So there's no x, there's one leading x up top. Then go to the next row and clear the second column. And if we have 4 variables or more equations, you work sort of from the top to first row, go down to the second equation, clear the second row, go down to the third equation, clear the third row, and then you get to echelon form. So that's the strategy. You could make any row operations you want, and sometimes there's unusual paths that allow you to avoid fractions. So there's like it's like an art form, like a skill. How can I get to the answer and do it as simply as possible? Like I've seen people where I could do it in like 3 or 4 row operations, but they took 10 because they weren't sure what exactly was going on, and they sort of went around in circles, but they were still doing row operations and they got the right answer. It just wasn't efficient. So there's 2 things. One is doing the row operations without making mistakes, and sort of having a strategy. Questions, or are you guys okay?
I actually thought about this just now. Would squaring be considered like if I need to multiply a row like by 2 by 3?
What do you mean squaring?
Would squaring a row be something that you can do or not?
You can only do 1 or 3 things. You can multiply 1 row by a constant number.
Okay, yeah, by constant.
You can swap 2 rows, change their order. Okay, swapping 2 rows sort of seems silly, right? If you just write, it looks like, who cares where you wrote it on the page? But since we're saying, well, the solution of the system is a triple of numbers, S1, S2, S3, such that this equation is true, and this one is true, and this one is true, the swap operation is based on the logical fact that P and Q is equal to Q and P. Okay, so this logical fact that this is always true and can be extended to more, like P and Q and R, the order doesn't matter. That's what's behind the swap. Now, the multiplication, you can see that if I multiply by a non-zero number, I can't multiply by 0. That would just kill the equation, right? That would remove it from the system. But I can multiply by any non-zero number, and that's not going to change the solution. But the crucial one is the row combination operation, which allows you to take any row, in your mind, multiply it by a number and add it to another row. Okay, so for example, here, we're going to do, and here's our notation, we're going to do minus row 1. See, here's row 1. Row 1 is a name for this equation. Row 2 is a name for the second equation. Row 3 is a name for the third equation. Okay, so I'm going to say, I'm not going to change row 1, but I'm going to multiply row 1 by minus 1 and add it to row 2. And this is the new row 2. This is my notational convention. For a row combination operation, I can have like any number R times row 1 plus row 2. I cannot change this sign. Some students like to, these are elementary row operations. Some students like to try writing R times row 1 minus row 2. That's really two row operations. That's saying I'm going to multiply row 2 by minus 1. Then I'm going to add minus R1 to that scaled one. So we're going to deal with what are called elementary row operations, in which you can't change this plus sign. And the second one is always the one that gets modified. That's just a notational convention. So we're always on the same page. Okay, so let's do this. So what I can do is I have to copy the first row and the third row, because those don't get changed. But I do change the second row, and I'm going to, so I can do it term by term. Minus x plus x is 0. Minus y plus minus y is minus 2y. And minus z plus 2z is z. And minus 6 plus 4 is minus 2, if I've done that correctly. Now, there is something, notice that this operation just involved the first one and the second one. Well, so I can, in one tableau, one sort of image like this, combine two row operations. What I'm going to do is I'm going to actually also change do a second row operation, which is row 1 plus row 3. Okay, now I can do these because they don't interfere with each other. I can do this, and I can see completely how it went. I don't want to be able. Don't want to do two things in one sort of row like this. That where I have things that depend on one another. Where you did it on paper and then wrote in the result. Okay, so it's like those two row operations don't affect one another. But I can say, okay, row 1 plus row 3 is x plus minus x is 0. Y plus 2y is 2y. Y plus y is 2y. Z plus 4z is 5z. And 6 plus 8 is 14. Okay, so the claim is this linear system is the same as this linear system in the sense they have exactly the same solution set. So I could say, well, this is the solution set where row 1 is true, row 2 is 3, row 3 is true, and this is the one where these three equations are true. Now, when I go on and do my next row operation, I'm going to call this one row 1, this one row 2, this one row 3, even though they've changed. So the previous one, the row 1 is always the first row, the second row, third row. Even if you swap them, they're attached to this equation. They're just saying the row on top, the row in the middle, the row on the bottom. Shruti.
I think the last equation, row on row 3, is actually just 5 equals 14. I don't think that there's a 2y there. With this row operation. Yes.
So I do x plus minus x is 0. Y plus y is 2y.
Plus 5. Okay, sorry about that.
Okay. No, that's good. I'm glad. Okay, so now this is not an echelon form yet because I've cleared. See, I used these two operations to clear the first column. So I have x with 0 and 0 under it. But now this one, the leading term in the third row is underneath, not to the right of the leading term in the second row. So this leading term here doesn't have zeros underneath it. So this is not an echelon form, so I have to keep going. But what I can do is take row 2 plus row 3 to go there. And so this isn't going to affect the first row, so I'm going to put x plus y plus z equals 6. And then I'm going to leave off the 0, and it's not going to change the second row. Minus 2y plus z equals minus 2, but minus 2y plus 2y is 0 there. And z plus 5z is 6z. And minus 2 plus 14 is 12. Now that's an echelon form. So this is in echelon form. And that's the goal, echelon form. And once we get to echelon form, we can identify leading and free variables, okay? So the thing you can do now is identify leading and free variables. Now, a leading variable is just one that has a non-zero coefficient in a row. So here, X is leading in the first row, Y is leading in the second, Z is leading in the third. So X, Y, and Z are leading, right? And there's no free variables, no free variables. Now, you can see then that what we do then, in this case, once we get to echelon form, we do back substitution. Now, so this is still what we do is we start with a third equation and work upwards. So the third equation is going to be, we solve, you can see this is going to be Z equals 2, right? The third equation yields, by dividing both sides by 6, I get Z equals 2. And that was the whole point of echelon form, is that the third equation can't contain any X's or Y's because I've made sure there were zeros here and here. Okay. Then I can write down the second equation. It's back because I came downwards here, then I'm going back upwards. Well, it's minus 2y plus z, that's plus 2, equals minus 2. And so this leads to y equals, well, I subtract minus 2 from both sides, I get minus 4. The minus signs then would cancel, and I would get, I think, y equals 2, because if I put back in 2 times minus 2 is minus 4, minus 4 plus 2 is minus 2. So I've got z and I've got y, and I do the first equation, which is x plus y plus z equals 6. Well, y, that's going to become x plus 2 equals 6. Well, that's going to be 2 plus 2 is 4. I subtract 4 from both sides, so I'm going to get x equals 2. So it happens that, therefore, so there's only one solution, right? Because when all the variables are leading, it turns out there's only going to be one solution, because you can sort of see, if they're all leading, I can solve the last equation for z. I can get rid of z and solve this one for y, get rid of y and z and solve the first one for x. And that's going to be true all the time, that that in order to have more than one solution, you're going to need a free variable. Okay, so then what we're going to do is we're going to package up this by saying the solution set. The set of all solutions is, and we're going to package these three numbers as a vector. So it's going to be 2, 2, 2, just like that. So that's the answer. Now, what you want to do if you're solving, so what I'm looking at is not you're finding the answer. I mean, I can show you, we can put this into an algebraic manipulation program and just find the answer. So there's no, it's like knowing the answer isn't, so what I want to see is that you understand how to do Gauss's method. So for example, what we'll do in the assignment when you work a problem like this is you'll write a sentence, have a math block, like for example, this whole Gauss's method thing would be a math block. Then you have a sentence that says, what just happened? I found echelon form. Then you would write in, okay, now we're going to do back substitution. You describe what you're doing. So someone reading your solution would be able to sort of understand what you're doing. So you do back substitution and you'd say, the third equation leads to this value, the second equation using this value in the second equation gives this one, which yields this value, and doing use in the first equation, we substitute X and Y as 2, and we get this last, so you use some words to describe. Now, there's three, in LIX, there's 3 environments. There's EQN array, display environment, inline environment. So you can put some of simple equations in line, bigger equations sort of display them on a line of their own, and then we always do Gauss's method in the same pattern like this. Okay, so that's a model. That's exactly what I want you to be able to do on the first demonstration, and what I want you to be able to do on the first assignment. And if you master this, then we'll be doing this throughout the whole course. So it's like a good tool. Okay, so before I try to get you guys to solve some problems, any questions? Okay, so let me